Good morning. Everybody ready? My name is Brian, and I'd like to welcome you and thank you for coming out to Blackhat, DC this year. This is track 2, Attack and Defense. We will start it off with Moxie and his talk on new techniques for defeating SSL in practice.
Hello. All right. This is a little unusual for me. I'm not usually on either side of this podium. I tend to shy away from these kind of things, but I thought I'd come check it out, talk to you guys, see what's going on. It's a little surprising. The keynote was on defending the militarization of cyberspace, which is unusual. 10 years ago, I feel like we would have been talking about protecting our communications from the state and the cops, not centralizing them in the hands of the state and the cops. So I think a lot has changed. But we'll see. So I'm supposed to talk to you about new tricks for defeating SSL in practice. And I've been thinking about SSL for a while. So I've got a bunch of tricks, and I'm not going to burn all of them on you guys today, but I am going to show you some things that are probably in the less technically complex area of my repertoire, but are still deadly in practice, I find. So we're going to start with the old and eventually come to the new. So the backstory is that I started thinking about SSL specifically in terms of SSL and certificate chaining. So I hate to break it to you, but SSL uses these things called certificates. Probably everybody here knows what they are and what they're for, what they do. But somewhat more specifically, you can say that generally there are two types of certificates. Certificates often come in pairs. You've got your certificate authority certificates and then your site certificates. The deal is that your CA certificates are embedded in your browser. They're kind of all powerful, and basically they only function to serve to authenticate the site certificates, which identify a particular URL, and they're known to be authentic based on the signature of the certificate authority. Sometimes the picture is a little bit more complicated. You might not just have two certificates. You can have a whole certificate chain. The idea kind of makes sense, right? Sometimes you might want to delegate your signing authority to a third party. But the third party doesn't have their certificates embedded in a web browser. So what do? The CA certificate signs the intermediate certificate authority's certificate, which then goes ahead and signs a site certificate. So you have these intermediate certificate authorities. Their certificates are not embedded in the browser. Their authority is based on the signature of the root CA. They're still sort of all-powerful because they can sign any other site certificate. And when you receive this, instead of just receiving two, you receive a chain. The chains can be longer than 3. In fact, they can be pretty long. There's no standard that I know of, but it depends on implementation. I think Firefox, the max chain length is like 20, 25, something like that. So you can have a lot of intermediate certificates in there, in which case you get this whole chain back. So the question is, how do we validate these things, right? Turns out that mostly everybody tells you kind of the same story. What they say is that you start with the leaf node, and you verify that the leaf node has the same name of the site you're trying to connect to. Then you check and make sure the leaf node hasn't expired. Then you check the signature on the leaf node. And if the signing certificate is in our list of the root certificate authorities, you stop. You're done. Everything's good. If the signing certificate isn't, then you move one up the chain and you repeat the process. So I find that when looking for security vulnerabilities, specifically like implementation-based security vulnerabilities, inconsistencies, that kind of thing. It's good to start with places where developers probably don't really know what they're doing, but feel really good about the solutions that they've come up with. So, for instance, in this situation, here's a little diagram. It's actually from IBM's current website about how to verify certificate chains. And they give you the same picture, right? You start with the leaf node, you work your way up. And it's really well suited for a recursive function, right? So this is, this is a situation where developers who might not understand the full scope of what's going on might implement this using a simple recursive function and feel really good about it. They think, man, I used recursion today. It was elegant and clean, slick. So the thing is that when people implement these recursive functions, they really focus on the signature validation, making sure that the signatures match up. But the result of this sort of naive attempt is that you can certify that a chain is complete, but really nothing more. So what I mean by that, so let's say that you have this chain. So you have a root certificate authority, a couple of intermediate certificates, and then the certificate for a leaf node, say for blueanarchy.org. It's a domain that I own. So if I'm the owner of this blueanarchy.org certificate, what's to stop me from doing this? Creating another certificate for a site, say paypal.com, and then signing it with my leaf node certificate, and then presenting the whole chain to a web browser or any SSL client. If you go back and you look at what people say about verifying certificate chains, we haven't really done anything wrong, right? All the signatures are valid. Nothing has expired. The chain itself is intact. And the root CA is embedded in our browser, right? Something must be wrong, though, because we just created a valid certificate for PayPal, and we're not PayPal. So the missing piece, the answer is a somewhat obscure field in the X509 certificate standard called the basic constraints. The basic constraints essentially serve to designate what a certificate should be allowed to do. All certificates should not be able to do all things, right? Certificate for a leaf node like blueanarchy.org should really only be able to authenticate blueanarchy.org. It shouldn't be allowed to sign other certificates or revoke other certificates. So there's this field that specifies what it is that certificates are supposed to be able to do. The problem is that back in the day, most certificate authorities didn't explicitly set this field. It would just be absent. So you get a leaf node certificate, and it just wouldn't say anything about constraints, right? So the sane thing to do is to assume that, by default, this is not sort of an all-powerful certificate, that maybe if nothing is mentioned, that you should be a little skeptical. But in addition to that, a lot of web browsers and other SSL implementations didn't bother to check the field, whether it was there or not. They just ignore it and do this sort of naive certificate validation attempt. So what that meant was that anyone with a valid leaf node certificate that they've purchased legitimately from VeriSign, any other certificate provider, can create and sign a leaf node certificate for any other domain. So if I get blueanarchy.org, I can create a certificate for anything and present it. No one will be the wiser. And so back in the day, when presented with this sort of complete chain, Internet Explorer, Conqueror, OpenSSL, countless other SSL implementations, they didn't know the difference. They just thought it was totally valid. So this vulnerability existed for a long time. Then, in 2002, Microsoft did something particularly annoying one day, and I sort of blew this up in response and published it. And Microsoft, responded to my publication and said, "Oh, well, this is a real vulnerability, but it's basically impossible to exploit. Nobody should worry." So I released the tool that exploits it. So that tool was called SSL Sniff, and it works like you'd expect. So let's say that you have your standard client-server situation, two parties trying to communicate via SSL. SSL Sniff would do a man-in-the-middle attack. So it would basically jump in the middle of the connection. And So on the client side, it intercepts the client's connection request to the server. And at that moment, it looks at what the client is trying to connect to, and on the fly, generates a certificate for that domain, and signs it with whatever leaf node certificate you give it, or whatever, any kind of certificate you give it. So you invoke SSL Sniff with some command line arguments. You say, OK, here's any certificate. And on the fly, it generates a certificate for the site that the client was trying to connect to, signs it with your certificate, passes the whole thing back to the client. The client thinks it has a valid connection now. Simultaneously, on the server side, you just make a normal HTTPS connection, or wait, not even HTTPS, just SSL connection to the server, and you send and receive data as normal. So the server doesn't think anything's up. It's got a normal SSL connection. And the client doesn't think anything's up. It's got this certificate chain that we've created and passed to it, so it thinks everything's cool. And of course, the problem is that in the middle of these two connections, you're decrypting from one side and then re-encrypting and passing it on to the other side. The data is in the clear. So at that moment, of course, you just log everything to disk and do whatever you want with the data. Or you can inject data or modify, do whatever you want. So what this meant is that back before, I mean, this is sort of a more general purpose tool, but back before people started checking basic constraints, all you had to do was pass SSL Sniff a valid leaf node certificate for any domain, and it would automatically generate the right thing on the fly, and nobody would know the difference. OK. So the question is, what's going on now? Is this thing still useful post-disclosure, now that things have been patched? And it turns out that it is. First, you'd kind of be surprised who still doesn't check basic constraints. I won't talk about that much more today, but maybe we can talk about that some other time. Second, in the case of HTTPS, even when people got warning dialogues in browsers that had been fixed, most of the time they just clicked through the dialogues. So a lot of people were using SSL Sniff in its original mode long after things had been patched, and with fairly high success rates, because people get these dialogues and they just click through them. There wouldn't be any problems. And then it's also still useful as sort of like a general man-in-the-middle tool against SSL. It basically does what you want it to do. And it's pretty versatile. So for instance, the folks that just did the MD5 hash collision stuff that they released at the Chaos Commuter Conference in December. I don't know if people heard about it, but they were able to create a rogue certificate for a certificate authority. And so once they had that, the question is, well, now how do you use this? How do you exploit this, right? And SSL Sniff is a perfect fit, right? You just pass SSL Sniff your rogue CA cert, and it will man in the middle all the connections on any network that are happening at any moment and get all the traffic. So you don't have to do targeted attacks. You don't have to do phishing attacks. You don't have to do stuff like that. Do you have a question?
How do you get the client with SSL Sniff? Are you phishing, or are you actually sitting somewhere?
Oh, right, yeah. No, phishing, I think, is too much work. Right. I mean, so on any network, there's any number of things that you can do to hijack traffic, right? So on like a local network or a wireless network, I think most effective thing is ARP cache poisoning. So like my machine has a MAC address, and people need to resolve the MAC address of the router to the router's MAC address, right? But if you just constantly send ARP packets onto the network saying, hey, my MAC address is for this IP address, machines on the network will cache that, and so they won't do the lookup, and they'll just start sending all your traffic to you. And then it's really easy. You just, you can flip your machine into a mode where it'll just forward all traffic except for the traffic you're interested in, and then it just passes that to SSL Sniff, and you do what you want with it. Right. Go ahead.
Just reminding, we got a lot of machines fixed from DNS cache poisoning. We didn't get all of them.
Yeah, DNS things. And the thing is, like, DNS cache poisoning, I mean, that's one thing, but if you're on the network, it's trivial, right? You just, watch for the request, and then you spook the response. You have everything that you need. So you can either hijack DNS, ARP, anything. There's many different ways. It's pretty non-trivial. And there are people that think that like switch networks protect them for this, but it doesn't. Anyway, so MD5 hash collision stuff, and there's actually some other cool stuff, other cool tricks that involve SSL Sniff that maybe we'll talk about another time. Okay, so I think this talk might be kind of a misnomer, because I think I'm going to focus mostly on HTTPS, not just SSL in general. So the question for me was, given this situation where we're trying to intercept secured web traffic, and right now, given what's been disclosed about SSL Sniff, a lot of browsers have been patched, and so people get these warnings, these dialog boxes, right? And a lot of times people click through that, but it seems like maybe we can do better. So the question is, what are some tricks that we can do to try and improve our odds? So way back in 2002, there are these people that had this TV show. It's called like Tech TV or something like that. And they wanted me to come and do a demo, like a live demo of intercepting secure traffic on a network. And so they wanted me to come down to their studio, and they had some machines set up, and I was going to set up my machine, and they were going to browse to a site, and I was going to like intercept their password when they posted it, right? And so I'm down there, and I set this stuff up, and I'm watching, right? And the site that they choose to go to is bankofamerica.com, right? Because I guess people care about online banking. You know, that's something that it's like a big scare, right? If your online banking stuff isn't secure, you're in trouble. So they choose bankofamerica.com. And so they went to the website, and this isn't exactly how it looks today. I modified this page, but it's close to how it looked then. And it was pretty interesting, right? So it's the situation where you go to the site, it's a normal HTTP unencrypted connection to the website. And on the front page, there's this column on the left that's asking you for your username and password, and then you're supposed to click sign in. So what's interesting is that there's all this rhetoric, right? They've got their little locked icon that says it's secure, all this stuff, right? They're really trying to convince you that this is okay, man, type this stuff in. No sweat, we got this under control. I don't know who invented the locked icon button, but that thing is, that's everywhere now. They really hit the gold mine with that. Like padlock, who would have thought? Anyway, so it doesn't inspire security, you know. Anyway, so they got this thing, right? And you know, we're supposed to click this button, but the thing is that it's a button, right? So if you mouse over it, you don't see the URL that it's going to post to in the status bar because there's a button, so it doesn't show you that. So it turns out that when you click the button, it does actually post to an HTTPS link, but there's no way to know that, right? Mouse overing it doesn't tell you anything. Really, the best you can do is try and view the source of the page to figure out whether that's going to post to something secure or not. But even that is problematic because most browsers, and definitely Firefox, will issue another request to the site to get the source to view. So it's like you can see the source, but this is not what's actually guaranteed to be rendered on your page, right? Because it's another request, right? There could be discrepancies. Attackers could do different things. Go ahead.
You also don't know if there's any other JavaScript on the page that's going to sniff the form as you type it in.
Sure, right. Stuff like that. So, right, okay. So it turns out that this pattern is totally prevalent on the internet today. You find it everywhere, right? Here's an example. This is a recent page, Wachovia, another online bank. I'm sorry to subject you to these things. It's kind of gross ads, but anyway, the same thing. Unencrypted site. They ask you to type in your username and password. Presumably it posts to something secure, but there's no way to know. They have their own little locked icon, all this stuff, telling us it's secure. Hotmail, same thing. Unencrypted site, they ask you to type in your username and password, post to a link. Maybe it's secure, maybe not. So anyway, this is actually all over the internet today, and I think people are pretty used to it, actually. So back then, in this TV studio, I saw this, and I was like, whoa, man, there's probably some generalizable attacks here. I mean, there's obviously some problematic stuff with these particular sites, but how can we generalize it? So let's start by kind of looking at what we're up against, looking at how browsers function, how they have functioned in the past, and how they function now. So in the past, I would say that browsers invoked what I would call a positive feedback system, right? So they would deploy this whole plethora of indicators to try and convince you that what you're doing right now is secure, right? They have all these lock icons everywhere. Stuff would change colors. all this crazy stuff would happen. It's like this whiz-bang environment that's trying to tell you, this is secure, you know? So for example, Firefox 2, this is a, you know, secure site, or HTTPS site at least, and it's Yahoo's login, right? And, you know, up the top, the whole URL bar turned gold, like the whole thing turned gold. There's a little lock icon on the right. There's a thing in the bottom right corner. And by contrast, if you went to something that was particularly suspect or, you know, maybe not kosher by Firefox's standards, it would just pop up a dialog, a simple dialog. And the interesting thing was that the default for the dialog that it popped up was accept the certificate temporarily for this session, which is why I think people would just click through these things, right? People do the default, right? Something pops up, maybe they don't understand it, they just click OK. So I think I would contrast that to now, where I would say that browsers have been developing what I would call a negative feedback system. So to me, they're making this transition from trying to deploy all this stuff to tell you that something is secure to trying to deploy all this stuff to tell you that there's a real problem, right? So all the little indicators have been toned down. You know, a lot of these positive feedback things have been disappearing, but the negative feedback stuff has really been ratcheted up. There's not just simple dialogues anymore in a lot of browsers. So, you know, for example, Firefox 3, same site, Yahoo's login thing. A lot of the stuff is gone, right? Like the URL bar, the whole thing doesn't change colors. The little lock icon isn't even up there anymore. There's something in the bottom right. And now they have this weird thing where like the background for the favicon, if it's transparent, will turn blue. But I don't even think most people know that that's true. Yeah, that thing's still down there. But so by contrast, you know, if you go to a site, this is just a site that has a self-signed certificate, right? It's not just a dialogue anymore. Certainly not a dialogue with a default that says, OK, click through this. It's like a whole thing, man. You know, Firefox, I think it's 5 clicks to get through this now. You got to click add this exception. No one's just going to like do this, right? No one's going to be like, oh, OK, I'll just click through this, right? It's like they're telling you there's a problem, watch out. Even in situations where it's like self-signed certificate, I'd like to be able to use sites that have self-signed certificates, but it's a hassle, right? IE is becoming the same way. It's not just a dialogue. It's this thing that actually renders in the page telling you you've got a real problem. So the conclusions that I draw from that are, first, these days, if we trigger the negative feedback, we're totally screwed. We're out of luck, right? But if we fail to trigger the positive feedback, maybe it's not so bad. My intuition is that people's use patterns now are just to like browse along, do their thing, and only really care if something's like catastrophic problem, look out, you know. That people aren't, you know, like really keeping the eagle eye for all of the positive indicators. So we should start by asking the question, how is SSL used? And this slide is kind of wrong. It should say, how is HTTPS used? Because that's what we're talking about now. So specifically, how is SSL used in the context of HTTP? And when you think about it, I don't think anybody types HTTPS:// into the URL bar anymore. I think it's very rare. And just as nobody types HTTP:// into the URL bar anymore. So I think the way that most people encounter SSL in the web environment is it really only happens in two places. Clicking on links and through 302s, through redirects, right? So basically, people are only going to encounter SSL by coming to a page that they render out, and there's a link there that says sign in or shopping cart or whatever, and then they click on that. That's when they hit SSL. Or when you go to a page like PayPal, where the whole thing is supposed to be encrypted from the word go, and you type paypal.com into the URL bar, and it sends an HTTP request to PayPal, and PayPal sends a redirect back to the browser saying, hey, this should really be SSL, and then the browser makes another SSL connection back out to PayPal. Those are the two ways I think that people encounter SSL in the world today. In the web, sorry. So what this means is that people only encounter HTTPS via HTTP. So maybe we can think about starting by attacking HTTP, if that's what it comes down to. So normally, when we're doing man-in-the-middle attacks on SSL, we go straight for SSL. We go straight after that connection. But if SSL depends on this other protocol, why don't we look at that first? So normally, this is an example. You have some secure connection, and we try and do our SSL Sniff magic. But what if, instead, we attack the HTTP connection directly? And by doing that, we're guaranteed to have a leg up when we get to the SSL part. So here's a first cut of what that might look like. So I've got another piece of software. It's called SSL Strip. And you can imagine a first cut of that looking like this. You do your man-in-the-middle attack on your HTTP traffic. And you watch the HTTP stuff go by. And you let everything go by except when you see secure links or these redirects, you just swap them out for the insecure lookalikes. So let's say that you see an HTTPS link go by. You just swap it to an HTTP link for the exact same URL. So it looks the same. It's just a different protocol. The same thing when you see the location headers. Right? So location headers are what will be in the 302 redirect that says that your browser should connect somewhere else. So if you see a location header for a secure link go by, swap it out. And the important thing is that when we swap them, we keep a map of what it is that we've changed. So then we keep watching the HTTP traffic. And when we see an HTTP request for a URL that we know that we've stripped, we know that we've swapped it, instead of just proxying that through as the unencrypted version, on the server side, we go ahead and make an HTTPS connection. So the server thinks everything's fine. It's got its secure connection. The client is operating in an unencrypted mode. Then we continue to watch the HTTPS traffic go by. And we log everything we want, of course. And then we keep a map of the relative links. So all the relative links that come back in the HTTPS pages, CSS, JavaScript, all that stuff, we keep a map of that too, because that's all stuff that should be secure traffic, but the client will think should be insecure traffic. So we keep doing this cycle on and on. So the result of this simple kind of first cut is that, one, the server never knows the difference, right? It's got an SSL connection. It thinks everything's fine. It doesn't know the difference between you and a client. And the client doesn't display any of the disastrous warnings that we're trying to avoid, right? No dialogues, none of this crazy stuff. And finally, we see all the traffic. So how does this first cut look, right? So here's an example. This is Gmail's login. This is the secure version in Firefox 3. And this is the strip version. It's not a big difference. It's pretty subtle. It's definitely no dialogue that's like, whoa, look out. Yeah. This is the secure version in Safari. This is the insecure version. I don't know if you noticed, Safari is really slimmed down on the positive feedback. If we go back, the thing that's supposed to tell us that this is secure is in the top right. There's a little lock icon. That's gone. All right, so this is an okay trick, right? We've managed to avoid all of the negative feedback, which was our initial objective. But some of the positive feedback would probably be nice, right? People want to see that lock icon every now and then. And, right, people seem to like the padlock, right? So it'd be nice if we could get that in there somewhere too. So a second cut. Let's do everything the same. Got our SSL strip. We're watching all the HTTP traffic go by, swapping out all the links, downgrading everything to HTTP. But now let's look for the favicon requests. So if you see a favicon request for a URL that we know that we've stripped, this is something that should be SSL but is not, we'll send back our own favicon. What should our favicon be? So here's another example. Again, same secure site, a strip version. It's not perfect, but it's kind of funny. This actually looks really slick on Safari. I don't have a slide of it, but it looks nice. At this point, we're doing pretty good, right? We've avoided the negative feedback of death that we cannot encounter at any cost. We can do our subtle man-in-the-middle attack via HTTP. And if we want, we can throw in a lock icon, because people seem to like that so much. The interesting thing is that for some sites, they provide no visible difference that anything is amiss, right? So here again is Wachovia, online banking, or whatever. This is the secure version. This is the strip version. Give it to you again. Secure. Stripped. Secure. Stripped. So what's also interesting is that what we really care about are post data, right? Data that is posted that should have been secure but is not. And so after we've got that, we can kind of duck out of the game. It doesn't matter. We don't have to pay attention to this stuff anymore. It might be interesting in some applications, but generally, that's what you want. So SSL Strip has a mode where you can run it, and after it gets the post data, it just ducks out of the game. It just removes itself, and everything goes back to normal. So on sites like this, you really never know, because you post the data, SSL gets it, and then just goes ahead and upgrades the thing to SSL. I'm sorry, SSL Strip gets it, upgrades the whole connection to SSL. So you post the stuff, and the next thing you see is a SSL encrypted page, and you think everything's fine. The sites themselves also confuse us. So here's a stripped version of PayPal. I chose to invoke it with the favicon replacement flag. Trying to sell us love or something, I don't know. Anyway, right. So the site has its own indicators, right? It's got its own little lock icon. How do they know? You know, they're just putting it up there, right? This is secure, don't worry, right? So, you know, you go to the site and they're confusing us, right? You know, if I strip this version and you go to the site, you might think, well, maybe this is one of those patterns again where it's unencrypted, but then I type in my stuff, and at that point it becomes encrypted. So when we invoke it with this mode where we just jump out of the transaction as soon as we've got what we want, it really seems quite normal, especially when sites are doing everything they can to give us the wrong information. So there are a few gotchas here when it comes to deploying an attack like this. The first is content encodings. There's all these content encodings that are difficult to parse, right? So stuff is going by, encoded in gzip, compress, all this stuff. It's hard to deal with. The next thing is secure cookies, right? So cookies that get marked with the secure flag, they aren't going to get sent over HTTP. So if all these secure cookies are going by, the browser won't send them out, and then that'll be a problem because nothing will work. And finally, cached pages are a problem, right? So like, if a browser issues a request with an if modified since header, and the server sends back a response that says no, nothing has been modified, if we've just started our attack on the network, then that's a problem because we didn't get a chance to swap out the secure links in that page that the browser now has cached. So the links will work, right, as they're supposed to. So those are all problems. There's a simple solution, and that's just strip all that stuff too. Right? So we see the traffic go by. If we see set cookie statements, just kill the secure bit. If we see content encoding and requests that we don't like, strip that stuff too. If modified since headers, get rid of those. We don't want any of this stuff, right? And that's not hard as long as we're already doing all this stuff, right? Another big problem is sessions. So again, the most interesting stuff that we care about is post data. Posts that would have been sent over SSL but then weren't. Particularly, we want the usernames and passwords, right? And the problem is that sessions often cause us to miss the login step, right? Because there can be a long-running session that someone has stored in their browser, and they go to visit the page, and they present the cookie, and the site just lets them through. Wow. We cool? All right. So sessions, they're a problem. Right, of course, in this little game, we can get the session cookie, which is somewhat useful, but it's kind of small change, right? It's not that great. Sure, you can get access to whatever account people are accessing, but the cookies expire. You can't be guaranteed that you'll have long-term access. And also, the real nice thing about getting usernames and passwords is that people reuse their passwords everywhere. So if you get their password to one site, you've probably got their password to 10 or more sites, which you can't say the same thing for a session cookie, right? So let's strip the sessions too. So what that looks like is now we do our man-in-the-middle jazz with SSL Strip. We get the request, and we look at the request, and if it has cookies, we just kill them. We send back a 302 for the exact same URL that the request was for, but with set cookie headers that expire all the cookies that we saw. So the result is that the client immediately gets this redirect for the exact same URL, but when it reissues the request, it doesn't have any of the cookies in the request, and in fact, the cookies just don't exist in the browser anymore. And the client never knows the difference. I mean, there's no way to visually perceive that this has happened from the browser. And then the problem is that we want to be maybe a little less sketchy than that. Sessions expire, and I think people expect for sessions to expire. Sometimes it's not always clear when or why they expire. All kinds of weird stuff can happen. You log into something from a different computer, and for some reason that will kill your session on the other machine. Maybe you cleared your private data, something happened, So I think there's an expectation that sometimes you go to log in your site and maybe the session won't be there anymore. But people don't expect their sessions to expire right in the middle of an active session, right? So if you're like buying stuff on Amazon and you click, I want this book, people don't expect for your entire shopping cart to just be gone at that moment, right? So the problem is that if we, at any given moment when we start hijacking traffic on a network, there's a chance that there's going to be active sessions. In fact, there probably will be. So you don't want to kill those because that looks weird. But you do want to kill the things where, when people access content for the first time in a while, right? So now what we do is SSL Strip has a command line option where you can specify essentially amount of time to wait before you start killing sessions. So the way it works is you immediately start stripping all the traffic on the network. You do all your jazz, right? But you don't touch the session cookies for 5 minutes or whatever length of time you specify. And you just watch them go by. And all the ones you see you mark as clean. You just say, all right, these are okay. They're in active use. We're not going to deal with them. But after the time is up, you start killing cookies. You just don't kill the cookies that you've marked as clean. And so the result of that is that the active kind of sessions that people are using when you start are preserved. Nobody knows the difference. But the longer running sessions where then someone goes to check their email and they haven't checked it for a while, those get killed and they have to log in again, at which point you get your login, you get their login and password. And it's not as suspicious, So just this simple version of this trick, I wanted to kind of gauge its efficacy. So I ran this on a Tor exit node for 24 hours. And of course, I ran it in such a way where I pipe all the output to a script that analyzes the data and then keeps statistics but just throws all the data away. Just pipes it to dev null. I like Tor. I don't want to screw with those people. So the results, in 24 hours, the script intercepted 114 Yahoo email logins, 50 Gmail logins, 42 secure posts to Ticketmaster.com. It took me forever to figure out what was going on with this. There's an incredible amount of traffic for Ticketmaster.com on Tor. It seems like it doesn't make sense, but I finally figured out that there's these people who have businesses where they spider Ticketmaster and then wait for the time when ticket prices are a certain price, I guess, and then the bots buy the tickets at that moment or whatever. But then Ticketmaster doesn't like that, so they have this thing where if they see a certain amount of traffic from an IP address in a certain amount of time, they just blacklist that IP address for 24 hours. So now the Ticketmaster spiderers are using the Tor network to jump from exit node to exit node so that they don't like no single IP address attracts that much attention. But it's kind of interesting, right? Because now if we control all the SSL traffic, we can manipulate the Ticketmaster bots or whatever. You know, like if we want to, we can just be like, oh, it's 50 cents for this ticket now. And then they're, at that moment, they buy the ticket, in which case we intercept the credit card number. You know, it's, so I don't know. It's kind of interesting. Rapidshare.com, 14 logins. You can imagine what people are doing with that on Tor. Hotmail, 13 logins. PayPal, 9 logins. LinkedIn, 9 logins. Facebook, 3 logins. And then countless other secure posts, right? So this aggregates to 117 email accounts, 16 credit card numbers, 7 PayPal logins, and then over 300 other miscellaneous secure posts. So that seems like it's pretty good, right? So the question is, what is the success rate? You know, these are some good numbers, but what's, you know, how many failures did we get? So I modified SSL Strip a little bit, and what I really wanted to know was how many people balked. You know, how many people got to this place where they were going to type in their credentials and said, wait a second, I'm not going to do that. And so what I did was I tried to keep track of the number of times that someone requested a page that had a secure post, that had data that would be a secure post that we stripped out. How many people went to a page like that and then didn't enter their information? So I ran that for 24 hours, and I got, you know, similar success numbers. And then the result was 0 people balked. Not a single person went to, in 24 hours on the Tor network, went to a site that had secure login credentials and then didn't log in. I had to like test this myself to make sure it was working. I like pegged my Tor client to the exit node, because I tested it locally, and I thought, well, maybe it's something about Tor or whatever. And you know, you kind of think Tor users are more security savvy than most people. And there's been some evidence that that's not true, but than most people, you would think. Anyway, maybe it's the Tor network is so slow that by the time you get to the site, you really want to type in your stuff because you don't want to wait for it to, I don't know what it is. Self-selecting sample, I guess. All right. So we've got this kind of like simple version of things. Where can we go from here? It turns out that once you start kind of attacking this communications in this class, there's all types of ways that you can make this even more effective. And I'm probably just going to show you one of them. And that is combining this technique with homograph attacks. So, you know, there's the standard homograph attack, right? The problem is that sometimes the glyphs for different characters actually look alike. So this thing, paypal.com, looks like paypal.com, but it's actually paypi.com. And of course, the problem is that the glyph for an uppercase I looks the same as a lowercase l, right? And there's, you know, to the human eye, it's difficult to distinguish. So these, you know, this problem has been around forever. It's like, you know, also the origin of elite speak, which is great. But it's been made more interesting by IDN, internationalized domain names, because suddenly it's possible to register domain names with all kinds of characters. And so, you know, that's old news. You know, in 2005, this guy Eric Johansson registered a domain, paysomething.com, which uses the Cyrillic A, or it's not actually A, it's the Cyrillic character that just looks identical to A. And so it displays as paypal.com, right? But it's not. It's something else entirely.
He's been trying to give it back to PayPal for the same amount of time. So.
Okay, right. Yeah, they don't want it, but they, you know, they don't want it anymore because, well, there's some problems. Okay. Anyway, so there's some things that I don't like about like the standard homograph attack. One, the attack vector has to be targeted, right? So by registering this thing that looks like paypal.com, the only thing you can attack is paypal.com, which is kind of limiting, I think. And two, phishing is just too much work, right? Like, you don't want to get people to like have to go to your site to do the thing, you know. it'd be nice if you could just man in the middle a whole network and get whatever people are doing. Because a lot of times you don't know what it is that you want specifically. You know, you go to a network, how many people there are going to be using PayPal, you don't know. It has to be this really targeted attack, you know. It's nicer just to get whatever people are doing because a lot of times you find interesting stuff. And then the other problem is that the IDN stuff in this class has been fixed, right? So for TLDs like .com, Firefox renders the IDN characters as puny code, both in the URL and in the status bar, right? So it means it doesn't look so good. This is what the PayPal.com looks like today in Firefox 3, like modern browsers. The URL renders it out as puny code, right? So that's not going to fool anybody. It doesn't look anything like PayPal.com. It's this other expression that is used to do the actual resolution with DNS. And here, you're right, Eric Johansson's giving it back. So how can we reinvent this standard homograph attack? So first of all, we can't use .com or any of the TLDs that Firefox and other browsers will render into puny code because, again, it's not going to fool anybody. And secondly, we want something that we can really generalize. We don't just want like a simple substitution for some particular character in some particular domain. We want a general attack, right? So we start thinking, okay, well, what's in most URLs? Most of them have full stops, forward slashes, ampersands, question marks, all those kind of things. And if you look through the character sets that are supported by IDN and most browsers, there is a surprising number of lookalike characters for those things. So here's one way that we can deploy that. SSL Strip supports this. There's a nice little mode. You register a domain, something short, that's not in the .com namespace or anything, or any of the other TLDs that browser will render into puny code. So let's say we register something like ijjk.cn, something really short and innocuous, maybe a little bit obscure. Then you get a domain validated SSL wildcard cert. Wow, they thought ahead. All right. You get your domain validated cert for star.ijjk.cn. So that means that anything.ijjk.cn is going to authenticate fine with that certificate. And then you use your IDN valid characters that look very similar to forward slash, question mark, all of these things, to create false URLs. So then we run SSL Strip, and we go ahead and we man in the middle all of the HTTP traffic that's going by, and we swap out the HTTPS links as usual. But this time, instead of just swapping them out for HTTP lookalikes, we swap them out for HTTPS lookalikes. Right? So I'll show you what I mean. Let's say that there's this URL. This is the Gmail login URL. You can't really read that very well, huh? Anyway, if you look closely, you know, it's this thing, right? And you turn it into this other thing, gmail.com/account/service-login, question mark bang, ijjk.cn. And the deal is that these forward slashes aren't really forward slashes. They're characters that look a lot like forward slashes. So this thing displays the way we want it to in the URL bar. It doesn't display as puny code, but when resolved, it becomes this other thing, google.com, blah, 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 ijjk.cn, which happens to be a domain that we own and have a SSL certificate for. So when we man in the middle of these connections, we do SSL back to the client, and we can present our own certificate to the client that the client will then validate, and everything will be fine because everything is fine. So here's what it looks like. We've got a request. We do a 302 for the same URL, kill all the cookies. We get the request again without all the cookies. This means that we proxy a page back that has a login and password form that the user is going to have to fill out and type in. Then we get an SSL request for the lookalike domain that we've swapped out. And we go ahead and complete that connection and proxy back data from the actual domain. So on both sides, we've got an SSL connection. The browser gets all the positive feedback, but it happens to be an SSL connection that we control. And of course, in the middle of these two connections, the data is in the clear, and we log whatever we want. Go ahead.
You said there were IDN OK characters. You're saying that you can get characters in the status bar, or the address bar, that are non-ASCII?
Yeah. Yes, because they're for TLDs that the Punycode filters only do the Punycode swap for certain TLDs. .com, all this stuff. For instance, .cn, they do not do that for. And you know, the idea is PayPal.cn doesn't look that good, right? But this other thing looks really good. So here's an example. Here's PNC, another bank. This is the thing people care about, so I'm going to try and be inflammatory, put it in the slides, you know. Here's another bank. This is their standard version, and this is our version. It's pretty good. We still have the little blue favicon thing or whatever. That's the positive feedback that people want. And remember that this is only for one step of the process. As soon as we get what we want, we go back to the normal SSL. We just send them back over to the normal connection. So the nice thing about this, combining homograph attacks with the HTTP man-in-the-middle attacks, is that it happens in real time, right? You don't have to do these targeted phishing things. You're on the network. Whatever you see on the network is yours. Second, it's generalized, right? Targets whatever people are doing at any time. And it doesn't require multiple certificates. It doesn't require restricting ourselves to popular sites. It's really inexpensive. You just get one certificate and you're done. And of course, once we get the secure posts, we can switch them back to a normal traffic stream. The other thing that's interesting, go ahead. Yeah, it doesn't work in some browsers, but it works in Firefox fine. Yeah. So, right, what was I saying? Oh, yeah, the other interesting thing about like this particular variant of this attack is that one, so it works against other stuff, like this will defeat perspectives, which some people might know about. It's an alternative certificate validation system. I also really like EVP for this. First of all, EVP seems like a weird thing. Do you guys know what that is? The extended validation thing where like now the big green thing shows up or whatever. It has the URL. To me, this seems like a joke, right? Where it's like now we're supposed to pay extra for the certificate authorities to like do the thing that they were supposed to do to begin with. It seems like it's like classic security, right? Where it's like there's classic software, I guess, where it's like people expect for it to be broken and then they'll pay you to fix it. It's like your own software, you know. Anyway, so this works for EVP too, right? Because it's like you can get your EVP cert for the domain that you legitimately own. Call your company Ultra Secure Communication Incorporated, right? And that whole thing, Ultra Secure Communication, is going to show up in the URL bar. And the nice thing about that is it's going to push all of your IDN characters off the edge of the URL bar. People won't even see them, right? So it's anyway. Okay, so I think it's about 15 minutes left. There's a lot of other places that we can go from here. This is just a start. This tool has a lot of other tricks up its sleeve. I'm just going to leave you with these. I think the lessons of this are that lots of times the security of HTTPS comes down to the security of HTTP, and HTTP is not secure. And if we want to avoid the dialogues of death, just start with HTTP, not HTTPS. And once we've got control of that, we can reintroduce all the positive indicators, whatever we want to do to get people going. Yeah, other tricks. I'm going to jump right to the end. Okay, so this tool, SSL Strip, is going to be on my website. Probably tomorrow. I'll put it up there somewhat reluctantly, but there you have it. Questions, comments, thoughts, concerns? Yep.
Client certificates defend against this so rarely used.
I'm sorry, what?
Client certificates defend against this if the bank wants you to plug in with a client.
Oh, yeah, that's true. Right, client certificates. I haven't thought much about that. Pardon? Right. This gentleman was saying that client certificates might be a good way to defend against this. I think my intuition is that that's true. I haven't really thought much about it because I very rarely see that pattern, honestly. Yep.
Some of my customers have a pattern of they'll put an SSL breaker so they can see all traffic coming across their gateways. Are there implications positively or negatively for these attacks when you're sniffing, when you're turning all traffic into HTTP yourself and then back into HTTPS?
So I'm sorry, you're saying your customers have like
firewall and they want to sniff all traffic, including SSL traffic. So they'll break it up. They'll
Oh, I see. Yeah. So you're saying that they'll man in the middle all the outgoing connections with their own certificate? Right, right. I mean, I wouldn't use those networks if if I worked there. I guess I'd have my SSH tunnel somewhere else. But you're saying what are the implications for this technique in that situation?
Attacks easier, harder, just different?
They're probably easier. I mean, they're certainly no harder. All that they're doing is introducing another kind of chink in the armor, I would say. They're just as effective.
I'm just thinking that browser could, or that gateway could block all those IDN characters, the homographs.
Sure, right. You could try and do something smart. Sure, I mean, right. It's easy to get into an arms race here. For instance, once you know about this, you can start looking for this, right? But it's an arms race. Yeah. Yep.
Have you found a way to get around domain highlighting in new browsers? For example, the last attack you just presented, right? If you look at Chrome or something where they highlight specifically the domain portion of the URL, right? And that'll show up very differently to a user.
Right. I guess I've never seen that. You're saying that was in my slide?
Yeah, no. If you go if you look at Chrome, and I think it does it and other stuff, right?
Sure.
What they do is they actually highlight the portion of the URL that is the domain.
That's clever.
Right? So you'll have a yellow highlight over it.
Yeah, right. So there's an example of people trying to give the positive feedback, I guess, which my intuition is that's on the way out, but those sound like new features. I've never used Chrome. It sounds scary. It's owned by Google or whatever. Yeah. Okay. Good idea.
Thinking about the way certain sites like banks will send you back your favorite picture, just to prove it's them.
Yeah.
How would this work in that environment?
It works fine. I mean, that's the nice thing about it. We're not trying to replace Bank of America or whatever bank. The deal is we're just proxying all the data through. The bank sends the favorite picture to the client. We just send it on to the client. We don't have to try and come up with the picture on our own because we're just sending data back and forth. And I mean, as an attacker, I really like those schemes, right? Because they make people feel warm inside, and it's nice to know that I can just proxy the favorite picture onto the client, and they'll be happy. Yep.
Is there something that you think browser vendors should be doing to secure HTTP, or something that some kind of standard to secure HTTP, or should HTTP maybe be secure by standard, such that it can be secured?
Yeah, I mean, it's kind of too late for that, right? I mean, so the real fix here is encrypt everything, right? I'm sorry. All right. His question is, should browser vendors be trying to change HTTP or make HTTP more secure, do something to HTTP to protect against these attacks? And I was saying I think it's kind of too late for that. That the answer here is that the fundamental problem is that when you have a secure protocol that depends on an insecure protocol, you just attack the insecure protocol, right? And so the answer is encrypt everything. But as long as the default, when you type in bankofamerica.com into your URL bar, is going to be HTTP, then that's a problem. And people have all these reservations about encrypting everything. It used to be that there was all the server load issues or whatever, but it seems like that has mostly gone away. There's all the stateless resume stuff now that servers can do. It seems to mostly alleviate most of those problems. I mean, if I were trying to design this, I would say, secure everything.
So that's the alternative question, right? Not what should browsers be doing, but what should the site owners be doing? How should they be designing their sites so that you can see some kind of more positive feedback or more negative feedback?
I mean, the question is, what should the site owners be doing to change their sites to make them look more secure, or to not look more secure, to be more secure, to provide the positive feedback that tells users what's going on? And I think my slip was the answer to that question, right? Which is that sites can do a lot to make them look more secure. You can put the little like icon on there. You can put something that says this page is encrypted, But again, it's an arms race. Whatever the site puts on the HTTP, we can strip out. If they put something in there that says, please look up to the URL bar now to make sure that it's HTTPS, we can just get rid of that.
So is the solution then to get rid of that behavior that people have of going HTTP blah, 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 bankofamerica.com, and to train people to say HTTPS //bankofamerica.com?
That would work. I mean, that would be nice. I mean, of course, like I said, there are other SSL vulnerabilities that maybe we'll talk about another time that would work in that situation. But yeah, it's a lot to ask, right? I mean, because people don't type http:// they type paypal.com. That's all they type into the browser, right? And as long as people are doing that, and as long as the defaults are what they are, then this is what you're going to see. Go for it.
So just a comment. So Adam Barth and Colin Jackson, actually a couple of web security guys out of Stanford, and to solve the problem of people just type in PayPal, their approach is actually to have, if we actually did have DNSSEC, actually have a record in DNSSEC that said, at the time you got the IP address, by the way, there is no HTTP version of the site. There's only an HTTPS version. And that actually seems to be the secure bootstrapping we're missing.
Right. So the comment is that there's something you can do in DNS if DNS were somehow magically secure that that indicates to the client that the site that they're accessing should only be accessed securely. I mean, I don't know the details of how that works, but the problem is that there are HTTP versions of these sites, right? Like there is an HTTP version of PayPal.com. What it is a redirect header to the HTTPS version, So it's like, again, it's an arms race where like PayPal can, one, just disable those redirects. It's probably not good business. Sorry?
Even if they disabled it, that doesn't mean you couldn't create one.
Right, exactly. You can create your own. If the redirects say, I'm sorry, you've got a problem, we're not going to redirect you, please type in this URL or whatever, you can manipulate that. You can turn it into a redirect if you want, it's pretty problematic. All right, you, and then you.
Any particular gotchas with SSL VPN clients besides the quick handoff? Have you other credentials?
Any particular gotchas with SSL VPN clients? So this attack is focused on HTTPS, right? Like, if you're using SSL for...
Or the clients that download from the web interface, and that's your initial vector for getting VPN clients.
Right. No, so that should be fine, right? Because those clients... Oh, download from web interface, right? Well, yeah. Yes, there are gotchas, right? Like this is... if the web interface is accessed in such a way that you type in a URL, it gets resolved to HTTP, redirected to HTTPS, and then you go to the site where you download the client. Obviously, at that point, you have control, and you can do whatever you want to the client as it's coming down. Yeah. I'm sorry. Okay. There, and then you. Yeah.
If the fundamental problem is people typing in PayPal.com in the browser and it defaults to HTTP, it seems that the solution would be for the browsers to implicitly go to those base domain names with HTTPS and say, what are the security relevant portions of the site? So that, like for sites that don't actually want to encrypt every single thing, this way if you get referred off the site,
right.
And restrict, you would get.
Right. So the comment was the browsers, when you type in paypal.com, should first make a secure connection to the domain and ask the domain, hello, how should we be communicating with you? Should we be communicating using only HTTPS or is HTTP okay? You can try that. The thing is that unless you customize that for a specific list of sites, okay, whenever we see PayPal we do this or whatever, and certainly someone should write a Firefox extension or something that does that or just does the right thing. Unless you customize it, then you have to allow for the fact that some sites might not support that protocol, right? So it's like if, and then what do you do when a site doesn't support that protocol? Well, you probably default to just allowing HTTP, in which case, as an attacker, all I have to do is DOS the request. And it's like, oh, well, they don't support that protocol. Let's just do HTTP. And then I'm sitting pretty again.
I'm not sure if Yahoo still does it, but at some point in time, I remember they had a JavaScript encryption going on. If they still do that, did you substitute out the JavaScript and then run it on your man in the middle, or what do you do in that case?
I haven't seen... I haven't seen Yahoo do anything like that. I didn't know about that, and I didn't do anything special for them. So either that doesn't exist anymore, or it's just magically defeated. I don't know what it was that they were trying to do. But again, you get into the situation where it's like, okay, these site owners can put some custom JavaScript or whatever into their stuff, but as long as we control what the browser actually gets, we can just delete it. It's an arms race, and the odds are in our favor, right? Because it's a big deal for them to make changes, and it's really easy for us to make changes. So,
could browsers defaultly try to get onto the secure site, and if that doesn't work, then they reverse it, so they're always going for default, and then you don't need to worry about the special protocol for preference. You just say whatever.
Right. So the question is, couldn't browsers always default to the secure version instead of the insecure version? And the answer is we would just DOS the secure version, so they have to fall back to the insecure version. And, go for it.
So once you have DNS stack deployed, what you should do is put the public key or the fingerprint of your public key of your SSL Strip into DNS. And then you have an external verification that the attacker can work on.
It's a good suggestion. Once secure DNS magically exists, you've put the public key of the site certificate that you're trying to connect to into the DNS record that way. You know what it is that you're trying to connect to. And, it's a good idea, and there's probably going to be problems there once you start to complicate these things by involving more and more protocols, there's inevitably going to be inconsistencies in ways that you can edge into that. But it's a good start. Okay, you and then you.
Solution sounds like for any site owner to never have both an HTTPS and an HTTP version of their page around. If it's supposed to be HTTPS, support only that one.
So the comment was that site owners should only support, if they want it to be only HTTPS, they should only support HTTPS and not even have HTTP around. I would say that, first of all, there's a lot of sites that don't want to only support HTTPS. You look at all these email logins, stuff like that. They only want HTTPS for some limited portion of the traffic because they don't want to have to deal with it for all of their traffic, which I guess I can kind of understand. The other thing is there's these other sites, PayPal, etc., who really do only support HTTPS, and the problem is that there's no way to really tell people that in a way that they will know or remember or whatever. Certainly, if you're PayPal, it's not good business to just turn off port 80 because then people will type PayPal.com into the URL bar and it will say, this site doesn't exist anymore, and then people will go use Moneybookers or whatever their rival one is, So this is like business concerns. So their solution is to do this redirect thing. The problem is that the redirect thing has its own vulnerabilities. 1 minute. I guess you are the last question.
Well, as network administrators, do you think we should focus on preventing ARP poisoning attempts rather than wait for method for DNS or whatever, since that all seems futile at this point? You just focus on that for now within our networks?
So the question is, as system administrators, shouldn't we just focus on the vectors that people use to get in the middle of these things? ARP cache poisoning, DNS poisoning, all this stuff, right? I would say you could try, but it's really hard. Definitely, particularly with wireless, right? How are you going to stop someone from just wild ARPing on a wireless network? It's pretty hard. If you control like a switched, like cable-based Ethernet, then there are some things you can do to try and make sure that this doesn't happen. But on wireless, it's really hard. And then, controlling spurious false DNS responses is also really hard. I mean, we're not even talking about DNS cache poisoning. We're just talking about someone issuing the correct response with the correct sequence number and the correct source port number with no other guesses directly to the client that requested it because you saw it go by. So, it's good practice to try and eliminate those things, but in practice, I think it's very difficult depending on your situation. Okay, that's it. Thanks, guys.